Thank you very much for the invitation. It's a pleasure to be here with you today. The talk I selected is a parallelogram inequality for abelian varieties and applications. This is based on joint work with Richard Griffon and Samuel Le Fourn. Richard works in Clermont-Ferrand and Samuel in Grenoble, both in France. So let's start. I suggest the following plan for the talk. So I'll start with some motivation, diophantine problems. I selected one, in fact, but basically the whole motivation of this parallelogram inequality is really from various diophantine problems. And this is a little bit where I'm from, so I want to start with this. Then the second part, I will, of course, discuss the parallelogram inequality. First, explain what it is, explain the link with the previous section, and then explain also in the third part some applications, and then elements of proof. So I will give the idea that I have is to give you the strategy of the proof and enough detail so that you understand how we implement it. Basically, I collected some lemmas that we proved. I will not give the proofs of the lemma, but I will give you the lemmas, the statements, and how to use them to actually deduce the inequality in question. So let's start. What kind of diophantine problem would you like to solve? So I selected this one. If you start with a number field and an abelian variety defined over this number field K, you take a finite extension of the number field. This will be the rational field for points. So we take a look at rational points on this abelian variety A. And then in this notation, A of K is the group of rational points of this abelian variety. And then there's a famous theorem, the Mordell-Weil theorem, which states that this group is of finite type. It's finitely generated. So it has a torsion subgroup, and part of the theorem also explains that the torsion subgroup is finite. And then if you quotient the group of rational point by the torsion subgroup, you get something free, of course, and it's free of finite rank. So Mordell-Weil tells you that, in fact, if you want to understand all the structure of the rational points on an abelian variety, basically you need finite amount of data. You need the rank, you need the torsion subgroup, and then you also need the generators for both side of this structural theorem. So then, okay, having Mordell-Weil, of course, is a nice step, but the path to explicit effective Mordell-Weil is still, I mean, it's still not completely obvious. So you still need to describe the torsion subgroup. And then you also need to compute the rank. And then you also need, when you have both of these, you also need to compute generators for the quotient A of K by A of K tors. So rank is hard, of course. I mean, it's the topic of the Birch and Sunitzen-Dyer conjecture in Tate's version in the high generality for abelian varieties over number fields. This is a big open problem. Even for elliptic curves, we are still struggling. I mean, so that's the status. Even getting the rank is difficult. So generators is even harder. And then the torsion subgroup also has not revealed all its mystery. So a full description of the possible torsion subgroups exists for elliptic curves over Q, and then for elliptic curves over, so in dimension 1, over small extensions of Q, up to maybe, well, I mean, 2, we know that, quadratic ones. And then 3, 4, 5, we have nice results already. I mean, we have as a community, I mean, I'm not involved in this. But beyond that, for big number fields, or for big dimensions, so bigger than 1, torsion is still a bit of a mystery. So a weaker information, but still important, is how about the size of this subgroup? So that's what I'm going to focus on. Seems a bit more reasonable. Is it possible to bound the size of this group? The group is finite. Okay, we don't know the structure in general, but then maybe we know something about the size. So Even the size, in fact, is difficult. Even a bound on the size is difficult. Well, it depends what you really want. So if you want a bound that is very uniform, then there is a proof for elliptic curves over number fields, any degree for that matter. And the bound is very uniform. It does not depend on the size of the curve itself. So this is impressive. The size of the torsion for elliptic curve. This is something that is nicely controlled. Uh, but but in general, in higher dimension, we don't even have that. We don't know how to bound uniformly the size of the torsion subgroup. But what do we know? What can we do? So in fact, we can do something unconditional, and this is what we can do. So this is a theorem that I extract from Rémond, 2014. And there you go. A is an abelian variety of dimension G. So G is the dimension of A. And this subgroup is finite. The size of it, of this subgroup, is then bounded above by what? So some constant, well, I mean, an expression depending only on the dimension. An expression that is a bit complicated to the power 4g squared plus 1. And then you have the degree of the field of rationality of the point to the power 4g. Yeah, so you have three steps if you want in this bound. Some kind of torsion, the dimension is there. Some kind of a constant, the dimension is involved. Then you have something depending on A, and then you have something depending only on the field of rationality for the points. So this is nicely split. It is not uniform. We would be happy to have something not depending on A, but okay, the proof is already rather hard. And so the explicit kappa of A is given by Rémond in their paper. And as you can see, it's probably not sharp. Okay, that's I agree with this. There is still a degree of a base field, but this is the field of definition. Huh? So it's in a way part of the data of the abelian variety is the degree of the definition of the equations that you need to describe the variety if you want. So it's there, it is present, but the more complicated invariant is this one, the HF of A, and that's HF stands for the Faltings height. So okay, we have a bound. The bound is explicit, probably not sharp, and seems a bit complicated. In particular, I did not define the height in the sense of Faltings here. So maybe this needs a quick reminder. What about the Faltings height? So I intend to open a little parenthesis now and redefine the Faltings height so that we all agree. But the philosophy is really we want to take the size of the variety. So basically, this counts as the size of the variety. Okay. So what's the Faltings height? If you start with a number field, you take its ring of integers. Then this abelian variety of dimension G admits a Néron model over the spectrum of OK. And this Néron model has a neutral section because, I mean, each fiber is a group. So this defines the section. And then on this scheme, you can define differentials, and you can take the determinant of the differential bundle on the scheme. That gives you this omega A over S to the G. So the to the G is the determinant if you want. And then so this lives on this guy, on the scheme, and then you can pull it back to get something nicely defined over S. And this is actually a line bundle over spec OK. And what is it measuring really? Well, it's measuring in a way the size or the volume of the differential structure of your variety. Yeah. So this is basically the kind of information you get in this object. So now if you have a bundle, so the second part of this slide is general. If you have a bundle over spec OK, there's a way to measure its size. And how do you do this? You pick a S non-zero section of L, so an element that is non-zero. And then for every Archimedean place, you're going to fix a metric. So to measure the size, you're going to have to decide how you're going to measure distances if you want on your bundle. And then you will take the metric for each of the Archimedean values that I listed here. You take log of this metric. Remember, S is non-zero. This has a meaning. And then here you just take the quotient. So L is a line bundle over OK. So it means this is a finite quotient because you have something of dimension 1 over OK. You just quotient by something that is not trivial. So then this is what is called the Arakelov degree. Note that, of course, this depends on the choice of the metrics that you decided to put on your bundle. Yeah. So this is a definition for any bundle. Yeah, you can play that game. You measure its size based on some metric that are there to tell you how big things are. But we had a special bundle created here from the differential structure of our scheme. So of course the idea is clear. We're gonna mix the two, and this is the definition. Let's take the bundle we started with, the differential bundle, if you want, and then we need metrics. So let's metrize this bundle using this formula. This is the classical thing to do if you want. If you have some differentials, what do? You wedge them until you get a volume form. So if you have enough of wedge, then you can take the integral, and this measures in a way the volume of your object for the specific metric that is fixed here. And this is what is called the Faltings height. So the base field is a number field. We normalized here to get something that works well when we do field extensions. So this height is, as you can see, a bit of a complicated object. Let me put here two remarks. First of all, it does not depend on the choice of S. You remember we had to choose a section of the line bundle that is non-zero. This is not completely obvious, but it comes from the product formula that exists on the base field where we work, so the number field where we work. So it does not depend on this choice, so that is nice. It's rather canonical in a way. And it does not depend on any projective model. As you can see, we never saw an equation, which is in a way a bit sad in a diophantine problem, but somehow it's also very powerful. The reason why it was so useful in the history of diophantine problems so far is also because it does not depend on projective models. So I mean, it is an interesting object that has proven interesting stuff. I'm going to mention that in a moment. Just before, just to fix, if you have not seen this before, this Faltings height, in a way for elliptic curves, the definition of the height is essentially comparable to the height of the Jane variant of the curve. So that measures the isomorphism classes over k bar, and the log of the discriminant of the curve, so that measures the bad reduction over the base field. So if you have these two objects, and if you have an elliptic curve given by a Weierstrass model, these are easy to compute. Then essentially you're computing up to some constants the Faltings height. So for elliptic curves, it's not so mysterious. In higher dimension, I mean, this is a little bit more complicated to compare with because, of course, the moduli space is more complicated. So essentially, we're dealing with some kind of object that measures how complicated the arithmetic of the variety is. That's what you keep as an intuition. And so the fact that I mentioned a bit before, it was useful, yes, because this height satisfies a Northcott property. So the set of abelian varieties of bounded height, bounded Faltings height, with fixed dimension, fixed base field, and up to isomorphism, it's finite. And this fact plays a role in the proof of the Mordell conjecture by Faltings. So of course, it's an interesting object, also outside of this talk. So I like this object. So that was the end of the reminder. So that the definition you have here, and this guy will play an important role in the talk. So it was present in the bound of Gaudron-Rémond. And if you go and take a look at how Gaudron-Rémond obtained their estimate, Well, first of all, I have to be fair. In their 2014 paper, they don't only prove something about torsion, they actually prove many estimates on various quantities of interest, typically minimal degree of isogenies between abelian varieties, a la Masser-Wustels, minimal degree of polarization on a abelian variety, bounds on torsion, but various things of interest. And the proofs are a little bit intricate. So if you go, and I think it's a good idea to go and check what they wrote. It's actually you need a bit of time to go inside the paper. But one fact that they use to attain their estimates is this lemma, or this estimate that they prove. If you have now a subvariety inside A, they are able to prove that the height, in the sense of Faltings that we just discussed, of the subvariety inside A is controlled by the height of A, of the ambient space, and some error term. And the error term is this complicated kappa of A that I stated when I stated their result. So now, of course, I mean, this actually is not non-trivial. It's not easy to compare these two Faltings heights. And the error term is damaging the bound, of course. And one of the reason it's damaging, well, first of all, it's an error term, of course, but I mean, they use some kind of induction. And so each time you get this in the game, then you add in the induction process some log of kappa A in the game. So okay, the damage is there also and important because of the induction process as well. Yeah. But the better bound is known. So better bound, oh, Gaudron Rémond, that's 2024. So 10 years later, the first paper was in 2014. This is what they prove. So same subgroup of interest, the subgroup of torsion, the bound on the size is now still something that depends on G, still something that depends on A, so we did not achieve uniformity, but okay. And then you have a bound on a term on the depending on the base field on the field of rationality of the points. So the structure is the same. The bound is structured the same as the first one, but of course it seems that they improved quite a lot of things, as you can see, because well, first of all, the powers are not as big. But also, and more importantly, inside the H of A, the H of A plays the role of kappa of A before. There's no 1024 G cube. There's a lot of things that were improved. Yeah. So still, the height is there. The same Faltings height is present. Um, but the improvement, the quantitative improvement is big, is massive. I mean, if you take a look at the size of these numbers, of course, even for G is 2, it's really amazing the improvement that was made here. Now, I call this the technological jump. There are a few new methods they introduce in their new paper, of course, to improve in such a way. And one of the jump is the following. They're able to prove this inequality. So be careful in the definition. I took their notation in the definition of the height of A. We normalize here by 1 over the dimension of A. But I mean, dimension of A is G, but this is not a typo. I really place dimension of A here because I want to use this as a function of a variety, if you want. So height of B really sees here the dimension of B, yeah, in the H of B. So if you multiply the dimension by this quantity, then you get up to some little other notation, the height, the Faltings height. Yeah, multiplication of the dimension and the big H is really the Faltings height. So basically, they're able to prove that the Faltings height is less of B is less than the Faltings height of A. There's no error term. There's no loss. It's just, I mean, it's the perfect friend. I mean, you want to do an induction on the dimension. You're very happy to get something that looks like this. Yeah, there's no error that piles up, when you apply your induction. So this is nice. This is a nice improvement in the game. So let me summarize what happened. In 2014, that was the bound they proved. In 2024, that's the new bound. And as you can see, a lot of improvements were at each step, in fact, were made. And one of the improvement was actually being able to use this inequality. But this is not at all obvious. I mean, even the first inequality they were using was not obvious to prove. So this one looks like maybe a bit too good to be true. I mean, where does it come from? So that's now my motivation is try to understand how can you control the size of a subvariety by the size of the big variety. Yeah. So before going further, I mean, if you think a little bit old style with equations, and you have a variety defined with equations, and you define a subvariety by maybe cutting with a new equation, there's absolutely no reason why the subvariety would be with smaller height. Because when you cut, you can just add crazy coefficients in your new equation. So I mean, this looks like it needs some kind of explanation. It is really not obvious. Yeah. So, um, but so where does it come from? Oh, there you go. So maybe there's a hint. So that's my second part. So now we enter the topic really, this parallelogram inequality. What we have in mind is understanding the control of subvarieties. And now I'm going to present something that is called the parallelogram inequality, and there is a link, of course, to the first part that you will see a little bit further. So to explain the parallelogram inequality, let me define the parallelogram. So we start with an abelian variety A, and then let's imagine you have two finite subgroups, G and H. Then you can quotient A by G and A by H. And if you want, you may also quotient A by G intersected with H. That's also a subgroup, finite. And then you can also quotient A by G plus H, also finite. So this gives you a nice parallelogram, like a nice commutative diagram. Yeah. So what's the inequality? Oh, it's a theorem of Rémond. So this is a tribute to the work of Gaël that I admire quite a bit. So take an abelian variety A and then take two subgroups, so finite subgroup schemes, GH, inside A of K bar. So they are rational in the way that is defined by stability by the Galois group. Then the inequality we look at now is we have these four abelian varieties. Now, if you compute the Faltings height of this one and the Faltings height of this one, the sum will be bigger than the Faltings height of the computed with the intersection, so it's here, plus the Faltings height of the one computed with the sum. So it got this name of parallelogram inequality because of this, and also to remind you maybe of some, I mean, little billionaire stuff on vectors. You take a look at the sum and the difference of two vectors. You can link, of course, the norm if you have a Euclidean norm with the size of the vector. So it's a little bit similar to that kind of structure. So we have these four abelian varieties, and their heights are comparable in this way. So it's just an inequality, but it actually plays a key role in the improvement that was given in 2024 by Gaudron-Rémond. So one thing, I mean, it's not obvious that this would imply something about subvariety. Even if you're not an expert here, let me guide you on one thing. All these varieties, they have the same dimension. So I mean, if you want to control the size of a subvariety a priori, you need a bit more than just having a control on various varieties of the same dimension. Or you need a step, you need something. So I'll explain a little bit later. Okay, so what is the parallelogram inequality? Looks like a little bit of a technical inequality between four abelian varieties that are linked by isogenous. Basically, this is what you have in front of you on the screen. And if it was only this, maybe if you don't love height, maybe you would think, okay, fine. you have an inequality between some heights. But this is actually at the source of the improvements in the various diophantine problems. Okay, so this is the inequality. It's over number fields. This is what was used to improve the bound. Mm, I said that several times already, but here, let me just stress the word one. Of course, this is not only because of this that they're able to improve in 2024, but this plays a role. So I selected this one because I'm interested in the height. So yeah. All right. So my question now is, what about abelian variety over function fields? They also exist. They are also very interesting. They also have Faltings height, and it's the one defined just in front of you. So if you start with little k, a perfect field, you choose your best smooth projective geometrically irreducible curve, standard setting. You look at the function field of that curve, and then abelian varieties defined over k exist. If you take one of dimension g, it also has an Rémond model. It also has a sheaf of differentials. You can also take the determinant of that sheaf, and then you can take its degree. And so basically, we did the exact same thing in the number field case, except that here there's no metric because we don't have to worry about Archimedean places. So in fact, this setting predates Faltings. It was already studied by Parchin, Arakelov, I mean, people before Faltings, and Faltings generalized some of the ideas to the number field setting, introducing metrics, etc., etc. So in a way, there's a simplification in the setting because we now work without the need of worrying about the metrics. But there are, of course, complications on function fields, in particular because, as you can see, I didn't say anything about the characteristics. So now the setting includes characteristic P, and it means that suddenly we have inseparability issues. We have other questions that will arise in the study that we would like to carry on. So here is what we can prove together with Richard Griffon, Samuel Le Fourn from this year. Now, if K has positive characteristic, let me assume semi-stability. It's technical, but it's not a big problem because in general, if you try to work on some diophantine problem, getting semi-stability is about doing a finite extension of the base field. So if you're allowing yourself some finite extensions, you can always come back to that. So this is not a big assumption, but it is there. Now in zero characteristic, there's no assumption. Now, if I take similar kind of subgroups inside A, we are able to prove that the height of the sum of the quotient by the sum plus the height of the quotient by the intersection is actually controlled by the height of the two abelian varieties on the exact same parallelogram. So in characteristic zero, actually, this inequality, the parallelogram inequality, is actually an equality. So you don't lose anything in doing this sums of quotients. This is an interesting feature. So okay, so I mean, perfect. It seems like it's the exact same thing, right? I mean, we took the analogous height, we have the analogous inequality. So what's the big deal? Well, I claim it's a bit surprising, at least because this was not our target at first. Our target was to understand the variation of height in an isogeny class over function fields. So our first result was not this one. Our first result was the following one that I'm going to present. So before stating the result, take a moment to realize, of course, all these varieties we talk about, they are isogenous to each other. So you start with an abelian variety A, you quotient by a finite subgroup, then this is isogenous, the kernel is G, and then same for H, same for G plus H, same for the intersection of G and H. So they're all isogenous. So imagine if we had a theorem that would say, oh, but you know, if you are isogenous, then the height behaves in this direction and behaves in this way, is constant or is, half of it. Or I mean, if you have a result about the size in an isogeny class, you can already say something about these guys. Yeah. But what do we know about the size of abelian varieties when you move through isogenies? So an isogeny is a surjective morphism with finite kernel. It respects the group law. So these are also very important morphisms in the maps in the study of abelian varieties, also for diophantine applications, in fact. So it's natural to ask about the variation of height for various problems. Okay, so what can we say? So this is what we can say. Okay, it's a bit of a bigger slide. So let me go through it. So same with Richard Griffon, Samuel Le Fourn. What we can prove is the following. There are three steps. So start with phi. That's an isogeny between two abelian varieties, A and B. And and B are defined over a function field K. So which means K is equal to little k of C, C being projective, geometrically reducible curve that is smooth, like a previous setting. So now the first point is very nice. First point is, um, well, if you're in characteristic zero, nothing happens. So if you know what happens over number field, this is a bit surprising, but of course here we have no metrics. So the degree, in fact, is you can prove that the degree remains constant in through isogenies. So this is very nice. Why? Well, because of course now if you try to compare the size of any of these guys, well, basically number one of the theorem here tells you, well, they're all equal, so fine. So for characteristic zero, then there's no surprise. I mean, I was asking why is it surprising, the parallelogram inequality for function fields. Well, there's no surprise here. It's even stronger. Everything is equal. So, okay, this is not where the interest is. Interest starts here. So you see, second point now, I have K a field of characteristic P, function field of characteristic P. I assume A is semi-stable. This is the setting where we work. And now let me assume that phi, the isogeny we start with, is actually of a special type, FV. So F stands for Frobenius. We're in characteristic P. So of course the Frobenius will show up at some point. And then the Verschiebung, so another isogeny that is very important in characteristic P. So what is an FV isogeny? It's not standard definition. Let me define it now. So what it means is that you have a composition, so your isogeny can be decomposed as a composition of E times a Frobenius and F times a Verschiebung in the order you want. Yeah. So you're not forced to start with the Verschiebung or the Frobenius. You can start with whatever you want. You just count the number of time you will raise to power P and count the number of time you will do the Verschiebung. Yeah. So that's E and F. E is for the little F, the big F, and little f is for the big V. Okay, this is maybe not the best notation, but you understand. So this basically how many Frobenius you have, how many Verschiebung you have in your composition. Okay. So now we can compute the height of the target, and the height of the target is basically the height of the source times p to the e minus f. The fact that it's times, it's interesting. Yeah, it's nice because often when you compare size of isogenous abelian varieties, at least in the number field case, you have additive errors. But this time you have a change that is multiplicative. So, okay, so what does it mean? So it means that if you have, let's just take one easy example, you just do the Frobenius. So E is 1, F is 0. Then the height of B, the target, is P times the height of A. So not only they're not constant, but you see they can be increased by a lot. And then if you only have V as an isogeny, so then E is 0, F is 1. So suddenly the height goes down, and it's like 1 over P times the height of A. So it means that if you allow isogenies of this shape in your parallelogram inequality, well, I mean, this is not obvious at all that you don't have any kind of powers of P. I mean, take the Frobenius, iterate it 17 times and Verschiebung once, and then what will happen? I mean, this is really, I mean, the fact that you have this result tells you that you have to be a bit careful in dreaming about the parallelogram inequality in the function field setting in characteristic P. Yeah, even for this subclass of isogenies. So that's what makes the first theorem, the parallelogram theorem, surprising, in my opinion, because, well, I mean, it's not completely obvious to see how the subgroups will behave. In particular, there's no power of P on the inequality, even in characteristic P. So that's the second part. So now, third part of the theorem, I mean, there are isogenies that are not of this type. So over elliptic curves, it's easy because basically you can decompose everything with this type plus something that is biseparable. So then you're good. But in higher dimension, you need more. There are more complicated options. And so we also studied that. So there we do not have an equality. We have inequalities. But we can also prove that you're forced to have inequalities. So these inequalities are actually sharp. We have examples at each level of situations where you have that the height of the target is really smaller or really bigger up to some power of P. As you can see, the power of P now needs maybe a little bit of an explanation. So what do we have? We have an integer that measures the we call it the Frobenius height. So in a way, some kind of depth of the kernel. So the kernel is a subgroup scheme, and then it's killed by some power of the Frobenius. And this is what you measure by this delta P of phi. So delta P of phi is here to tell you, well, the kernel of the isogeny has a role in the game, and it's there. And then there's a hat, as you can see, and the hat is the dual isogeny. So the kernel of the isogeny has a role to play, and the kernel of the dual isogeny as well. So this point 3, as you can see as well, I added an assumption, ordinary. This was not added anywhere else, but it's added here, and it's necessary, in fact, if you work over any kind of isogenies in the super special or super singular kind of setting, then you have counterexamples, in fact. Yeah. You have situations where you have an isogeny, one height is 0 and the other one is positive. So then you will never get something with a nice control. Yeah. So this is also part of the game in the characteristic P. So the hypothesis is really necessary. So this is the result that we have for the variation of heights through isogenies. And I claim that because of this result, getting a parallelogram inequality is not obvious because of the powers that can appear for some specific isogenies in characteristic P. It's very easy for characteristic 0, but in characteristic P, it seems that something is happening. There's some kind of cancellation of powers in a way. Yeah. Okay, so where are we now? We know how the height varies in some isogeny classes. We have some varieties that are isogenous. We are interested in understanding if we can prove a parallelogram inequality in this setting. Not completely obvious because of this behavior. Let's see. So before giving you elements of proof, I would like to give you two applications of the parallelogram inequality to somehow answer a little bit my first part with the nice questions about diophantine problems. So you remember the key technical step in Gaudron-Rémond that was improved was the control on the height of subvarieties. So first corollary we have, and in fact it's very close to the corollary of Rémond. So we follow his proof on that one. Is the following. So K is a function field, but it could also be a number field. In that case, you have to change the name over there. Characteristic P Then we assume semi-stability here. Then, in fact, for any abelian subvariety B, one has not only that the height of B is less than the height of A, but the sum of the height of B and of A over B, this is an abelian variety quotient of A by B. Actually, the sum of the two is controlled by the height of A. So it's a bit more than expected in a way. If you normalize things correctly, then this guy is non-negative. And then you really have the control you want. But in fact, you have more because there are two abelian varieties now in the game. And this is reassuring, because the dimension of A is, let's say, G, and the dimension of B here as a subvariety is less than G, and the difference between the two is precisely the dimension of A over B. So the fact that we have this A over B tells us, oh, but there's a chance you can deduce that from some control on the size of abelian variety of similar dimension. If only we could put B and A over B as a product maybe or something like that, then we could maybe compare with A. So there's a corollary for a good reason. I will explain quickly. Of course, it's Poincaré. So if you played a bit with abelian varieties, this is a structural theorem. So what is this theorem giving us? You take an abelian variety A and a sub-abelian variety B, and then there exists a complement B prime such that you can describe A as the sum B plus B prime. The intersection between the two is finite, so it's not trivial in some cases. It's not only zero, but it's finite. But if it's finite, it's good because intersection of two abelian varieties will give you a group. Both are groups. And then it's finite. So you have a finite group. What can you do? Well, for instance, you can take a look at quotients with that finite group that gives you isogenies. So you see, having finiteness here is nice. It tells you you might be able to use it if you want to construct isogenies. This is what is done here. So define G to be the kernel of this map. So what is this map? I didn't define, but I'm telling you it's an obvious map because A is B plus B prime. So in fact, if you have two elements in B and B prime and you want to go to A, well, you do the sum. So because I mean this tells you what to do. So take the kernel of the sum, it's going to be finite, and then take also H to be. So you have to take a look at how you organize things, but take H to be the intersection of B plus B prime. This is a finite subgroup in B. And then on the other side, you take 0, the 0 B prime. So this is also finite. Now, what do you have? You have B cross B prime. This is an abelian variety. It's a product variety. So it's eligible to take a look at the parallelogram inequality on B cross B prime. And then we have two subgroups of B cross B prime, and they're finite. So now this is your G, this is your H. You compute G intersected with H, compute G plus H, and then you compute the four heights that are listed in the parallelogram inequality. And guess what? You find this. So, of course, after a little bit of work that is not too hard if you know a bit of Faltings heights properties. So it's a clever trick, and we learned the trick from Rémond, but we can use it, of course, in this setting because, well, we also proved the parallelogram inequality, so then we can use it as well in the function field setting. Yeah. So that's the first corollary, which means that it's possible to control the size of B by the size of A simply because we actually have better. This can be understood if you want, if you like exact sequences. You take a look at B goes to A, that goes to A over B, and then you have an exact sequence like that, and then the height is then super additive. Yeah, so it's actually a nice property to have. Anyway, so that's the first corollary. It answers the question: how do you get a control on the height of B by the height of A? If you have a parallelogram, then you can use this proof both in the setting of number fields. That's what Rémond did. and also in the setting of function fields, also in characteristic P, because we have it. Okay, so that's the first corollary. So now let me give as a little bonus, a little corollary on the Jane variant, because I like Jane variants. So let's take a look at the elliptic curves. The whole thing applies to elliptic curves. Of course, you don't have interesting sub-abelian varieties on an elliptic curve, but you do have still isogenies. So now if you take a function field, and if now I denote little h to be just the degree of elements in K, because they can be viewed as morphisms, so they have degrees. Then the size, I mean, if I take an elliptic curve E, the size of the Jane variant as viewed as an element of K of E over G plus the height of the Jane variant of E over H will control the two other ones. Yeah. So in fact, there is an parallelogram inequality in that setting, and the proof is rather easy. You just compare the two heights, of course, note. If you're not too tired with all these heights, is that this is H and this is also H, and they're not the same definition, of course, but in fact, the two elements are very, very close to each other, so it's not a big deal. Yeah. So anyway, for Jane variants, you do have a fun inequality that is not the same for number fields. You have to be a bit careful because the height of the Jane variant sees the metrics. It sees the Archimedean places or over number field, but over function fields, that's what you get. So fun little corollary that you can maybe use for something. Okay, so now I will use the final minutes to give you some elements of proof of the parallelogram inequality. Before starting this final section, I'm just going to say I think maybe depending on what you like to work with, maybe the proof is more fun even. I hope. Let's see. So let's go. So I'm going to give you the overall strategy, and then the proof is really by dévissage. So we're going to go back to some smaller steps, smaller situations. So you will see how. I'm going to give you 5 lemmas, and but the interest will also, of course, be the final slides where I use the various lemmas. So I'm not going to prove the lemmas, but they're accessible. The paper is available on the archive, and then maybe I can give you hints in the question session. Okay, lemma 1 is kind of a nice lemma. It's not too hard to prove. It says basically you don't want to keep track of this G intersected with H because it's heavy. The notation is heavy. So you can actually assume for what you want to prove. What do you want to prove, by the way? You want to prove the parallelogram inequality. Yeah. You can prove the parallelogram inequality for all the subgroups satisfying this. And if you can do that, then you get the general case. This is what the lemma says. Basically, I'm giving you a hint to prove it. It's not too hard. So, okay, so from now on, we may assume that, in fact, the intersection is 0. Okay, so that's lemma 1. It's some kind of reduction to simplify our life. Lemma 2. Oh, big diagram. So what's happening here? Lemma 2 I mean, it's a nice reflex. What we try to do is a proof about a statement that involves a group. So to try to advance on this proof, we take a look at what's happening if you have a subgroup of that group. And so here is what happens. So H is our group. We take a subgroup. They're both finite. Now, what the lemma says is the following. Imagine you can prove the parallelogram inequality here. This is a parallelogram of the shape that we like. Yeah. So G is finite, H prime is finite. Imagine you can prove this. And now imagine, second assumption, that you can prove the parallelogram inequality on this parallelogram. There's another small parallelogram here. Yeah. So be careful. This is the new abelian variety, and then it's quotiented by H, and then here you have to quotient by the correct group. This is the new finite group, and then you understand what's happening. So we have this new parallelogram. So if both small parallelograms are satisfied, then in fact, so does the big one. So you're interested in this big isogeny here, composition of the two, and here G. So if you have a situation that you would like to prove A over G, A over H, A over G plus H, in fact, you can decompose as soon as you find a subgroup. That is very nice if you have something like this because you can start to cook up some nice subgroups. If you have a complicated group H that you don't like, maybe it has easier subgroups. That's a little bit of a hope. So that's good to have. This lemma is good to have. Okay. So keep in mind, if we have subgroups, we can reduce the proof to smaller parallelograms. Okay, so now I have three lemmas that are, of course, a little bit more in the details. So if G or H is étal with étal dual, so now I'm using a bit more algebraic geometry, then in fact the parallelogram is an equality. So you don't lose anything, nothing happens in a way. All the heights are constant. Of course, you know where it comes from because of the other theorem on variation of isogenies in characteristic 0. In fact, in characteristic P, if you're étal with étal dual, it's the same. So okay, there's an equality sometimes if G or H is very specific. Lemma 4, a bit the opposite direction. So if you have a group, you can decompose it as étal and connected parts. So now if G or H is completely connected, then in fact, there's a way to prove the inequality. It's not an equality in that case, but at least it holds. So lemma 4 says if G or H is actually connected, then you're good to go. And the final one is if G or H is étal, but this time of order a power of P, so then the dual is not étal in that case, if the power is non-trivial. So then, in fact, we can also prove the parallelogram. So you see, the first lemma was a little reduction. Second lemma is saying you should take a look at the subgroups. And these three lemmas, they're in a way starting the dévissage. Yeah, they're saying if your groups are very, very easy, in fact, we can prove it. So now the goal is to try to understand how to complete the proof. So first of all, let me deal with characteristic 0 quickly, because in characteristic 0, you're étal with étal dual. There's no inseparability. So lemma 3, if you know how to prove lemma 3, then you prove it completely in characteristic 0. So the job is done. So now in characteristic P, you need to find the interesting subgroups. And this is what we propose. So we decompose H, for instance. H could be G, but I started with H. So H is here, and then inside you have 0. It's a subgroup, so you have the neutral. And then you take a look at what's the connected component of 0. So that's HGO. It's also a group. And then containing this guy, there's also an HP infinity that's the largest subgroup with order power of P. Of course, you recognize the kind of properties that we need if we want to use the other lemmas. So this is why we focus on these guys. And so the goal now will be to decompose the isogeny A to A over H into a product, this time of three isogenies, because we have these three subgroups. So I have a diagram. I gave it a name, le coup de grâce. So I guess it's very close to English. So coup de grâce is when you suffer, and I know some of you at least probably suffer a bit with all these heights. So coup de grâce is the end. It's you stop the suffering. So it's almost done. But it's also a little bit of a play on word because I find it very graceful. It's a very nice diagram. So le coup de grâce, what is happening here? You start with A and you want to understand the parallelogram with A over G and A over H. What do? You decompose A over H into the three smaller isogenies. So now we have three parallelograms and we need to inquire about the possibility of proving the parallelogram inequality in each of these parallelograms. So I give here the reasoning. I'm quick because in fact, each of them needs a little bit more. So you kind of need to understand several other stuff that I did not explain to prove them. But basically, In the first one, well, now you have connected the kernel because, well, that's what you define the H0. So then this gives you the property, the parallelogram inequality by lemma 4. So if you know how to prove lemma 4, you know that this works by definition of H0. In the second one, what do you have? Well, the isogeny itself needs, you need to look at it carefully, but it has a dual with a kernel that is étal of order a power of p. So in fact, for the dual, you're able to prove the parallelogram, and then you need to explain how to deduce it from the dual situation. So this I did not explain, but it's in the paper, of course. So then lemma 5 will give you the answer here. And then finally, well, if you quotient it by all the p power, then the order is co-prime to p. But that means that in fact your étal with étal dual, this is again lemma 3, like in characteristic 0. So there's no more inseparability at all because you just killed everything. So you also get it here. But now that you have it in all the small parallelograms, you get it for the big one because of lemma 2 applied here and then lemma 2 applied another time. And that's it. Thank you.